We're going to talk about geometric optics today. So first, let me remind you that if you've got this kid bobbing up and down in the ocean, here's a kid, and he's got one of these floaty things around his belly. Here we go. And there's an ocean here, and he's bobbing up and down. You know that there's going to be a wave coming out from him. Woo, like that. Woo, because he's a source of waves. Or if you have a cat screaming in the room, you've heard these cats, they can sound like small children being tortured if they're screaming, and maybe screaming inside a room, and so there's this wave of cat scream that goes out, and it looks like that. And where's the cat? Can you find the cat here? I can find the cat. It's probably right there, screaming, and this is the room, and this is the cat wave. So I guess I'm drawing peaks and troughs and peaks and troughs. Maybe every black line here in this series of concentric circles, concentric meaning having the same center, concentric. These concentric circles are all coming from a single point, and as that wave expands, I suppose, well, if there's a certain amount of energy being put out per unit time here, some power being put out by the tortured cat, then there's energy coming out, and that energy is contained in that wave, and as that wave gets bigger, 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 much like a balloon being blown up, the energy density, or the balloon material density, becomes thinner as the wave expands, and as the balloon expands, of course, balloons become thinner. So first of all, you know that getting further away from a source is going to amount to having less energy density. And in the sense of light, it means it will be less bright as you get further away. And there are questions about how far away you can see a candle and how bright a certain candle appears at a certain distance, and all that's rather complicated. But I want to go directly to light now. So many analogies with sound, though, so you can keep thinking about sound a little bit. So I'm going to say here's a source of sound, or light. And out from that source is coming energy. Energy is all like, I'm going to leave that source. But at the same time, there's also this wave, and the waves are kind of like this. They're like, you know, in some sort of an area sense, the waves look like this, and these are the wave fronts, and you can see that they are naturally getting bigger and bigger, and therefore decreasing the energy density, because the same energy that's in this wave must be present in this wave front right here, and it's much, much bigger. So there's an area here. Let me crosshatch this area, and that's the area of the wavefront. But notice the orientation. I'm trying to draw this as a curved wavefront, the surface of a sphere that is the size, that's this distance here. Let's label this distance as r. Okay, here's my point. The wave front is always parallel to the surface, and the ray of light or sound is coming straight out of the source. So we know that rays have to be normal to wave fronts. Okay, rays have to be normal to wave fronts. And I want you to think about the surface of this sphere. As this sphere gets bigger and bigger and bigger, let's continue this out a little bit more. We'll go out to maybe here. As the ray gets bigger and bigger and bigger, I want you to think of other spheres that are really, really big. What do spheres ultimately look like when you get really close to them and they're really big? Can you think of a really big sphere that you're really close to? I can. And I don't know much about you. I think that's rather creepy. I know absolutely nothing about you, but I know that you're very close to an enormous sphere, and that enormous sphere looks flat, Christopher Columbus. So you shouldn't sail to the west, because you'll fall off the edge. Don't sail west. My point is, if you've got rays of light coming out like this, as you get further and further away, each of these wave fronts, dang it, breathe. Each of these wave fronts begins to resemble, well, a plane. And so if you're far enough away from the source of the waves, then the rays look parallel And the wavefronts are also planar. Cool. So for instance, if we look at the sun seems to come to us with parallel rays, and you would think that based on, well, a lot of experiments that you could do. I won't go into detail on that, but that's because we are so fantastically far away from the sun. So the other thing we need to discuss before, okay, there are two more things. The two more things that we need to discuss before we go into mirror optics is, number one, there are two general classes of reflections. And I hope that you've had a chance to gaze into a still pond so that you can fix your hair, or seriously, you should gaze into a still pond right now. But reflections, you could also look into a mirror, or what else? A shiny piece of ice? I don't know what you want, but here, this is what you look like right now. Okay, maybe that's just my camera, but here's, it's a nice camera, isn't that? Oh, yeah, Toshiba, you should get one of those. The idea of reflections are, there's one type which I'll call diffuse reflection, and there's another type called specular reflections. That's hard to say. Specular. And specular reflections make images. And the way to make an image is to keep all the light rays nice and orderly. And guess what does that? This sucker right here forms an image because all of the light rays come in and go out in a very nice structured way. Would you say a mirror is generally very reflective? Yeah, you would. But you don't notice that it's very reflective unless somebody happens to be shining a light right in your face. Like, let's see if I can do that. Good, but usually, it looks rather dark. I mean, you see your face or something, but you don't see brightness. Guess what's, but agreed though, a mirror is very reflective. Guess what else is really, really reflective? You want to see something really reflective? Okay, there. This white sheet of paper is incredibly reflective. In fact, among the most reflective things in the universe is a product called Tyvek. You should get your hands on some of this. They sell it as a building wrap in the United States, and it is a very, 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 very white thing. So if you go buy a house that's just being built, and it's wrapped in this stuff, the house glows. On a sunny day, you can get blinded trying to work on a ladder with this stuff. It's also very slick. It has fluorine in it. It's really neat. But white paper is incredibly reflective. But does white paper form an image? You can't look into white paper and see anything except what's splattered onto the white paper. So no, this diffuse would be something like white paper. This is an example. For example, white paper. And specular reflection forms images. Now, I've got an interesting thing here I found. This is white paper, but it's also got a sheen to it. So I want you to begin to separate shininess from reflectiveness. Shininess, now I could, if I were very careful, I could probably form an image with this white paper because it's got a reflective piece of plastic on top of it. Can you see those streaks there? I hope that you can. I'm trying to get it so that you can see that there are lines that are reflecting the light. That's actually an image of those lights that I have up there. Okay, great. But here's the distinction. Specular reflection, if a reflection is specular, then a certain principle of reflection is followed. It's called the law of reflection. Boy, oh boy, it's a law, but you can break it. The law of reflection works like this. The incoming angle has to be equal to the outgoing angle. Theta initial is theta final, or some people like to say theta reflected is theta initial. Let's see if we can do the law of reflection with, ready? Pew! A laser. Check it out. Let me clear myself some space here. I have a mirror, and the light comes in, and the light goes out. Notice that I can define, let me go ahead and define this for you. I'll define you a normal to the surface. We're always going to be working from a normal to the surface. And if I have an incoming ray right here, and this is the initial angle, then if we've got a mirror here, let me see, I'll make the mirror like this. I don't know what I'm doing here. This can be my mirror. Then the outgoing ray has to leave at the same angle. Boy, I hope I got that right. This would be theta reflected. If this, golly, that's a terrible theta. If those are the same angle, then we're going to see that this is true. Ready? Let's see if I can get this right. There we go. Here we go. So you see that? Also, I can make them both bigger, like this, no problem. But the incoming angle is the outgoing angle. The light ray is like, or we can make them really sharp. It works everywhere on the mirror. It works over here too. Or over here. But the mirror is just really structured. Something comes in, it goes out at the exact same angle. The same angle away from the normal, and that's important. Of course, if you look at it carefully, you find that this angle over here, theta nothing, because I don't want you to think about it, is also equal to theta nothing over here. They're the same, but this is an important definition because we're going to work with it in a lot of other contexts as well. Okay, I think you understand this guy right here is called specular reflection. And the thing about diffuse reflection is if I shine the laser pointer on here, I'm like looking into it, and it's just moderately brighter than when I'm not looking into where the reflection should be. There is absolutely no stuff coming out of here. There's no awesome reflection or anything. Let's see. I mean, it's clearly a lot of reflection because you, the camera, are able to see where this dot is. So there's a ton of reflection. But the interesting thing about specular reflection compared to diffuse reflection is diffuse reflection, I can see this laser where it hits from any angle. So I want you to take a break. It's just step away from the computer and go look at your mom and ask her to stand still for just a minute and say, Mom, would you please stand still because I want to see if I can see you from other locations. So if you freeze your mom, so this is your mom here, and she's doing something, but you say, stop, Mom. And then you walk around her and you notice that you can see her from every direction. That means your mom must be a diffuse reflector. If your mom is a diffuse reflector, let's see, we can put this in insult form. Your mom is a diffuse reflector, and your momus. Wow, that didn't work out. Your mom is a diffuse reflector because you can see the light that's hitting her from any direction at all. She's not a specular reflector because you can't form images with your mom. That's kind of weird. But you can definitely see her from all directions, so you know that the light that's hitting her from anywhere, even from a single light bulb, is then reflected throughout the room. Awesome. And there's an ocean here, and he's bobbing up and down. You know that there's going to be a wave coming out from him. Woo, like that. Woo, because he's a source of waves. Or if you have a cat screaming in the room, you've heard these cats, they can sound like small children being tortured. If they're screaming, and maybe screaming inside a room, and so there's this wave of cat scream that goes out, and it looks like that. And where's the cat? Can you find the cat here? I can find the cat, probably right there, screaming, and this is the room, and this is the cat wave. So I guess we're going to talk about geometric optics today. So first, let me remind you that if you've got this kid bobbing up and down in the ocean, here's a kid, and he's got one of these floaty things around his belly. Here we go. Are all coming from a single point, and as that wave expands, I suppose, well, if there's a certain amount of energy being put out per unit time here, some power being put out by the tortured cat, drawing peaks and troughs and peaks and troughs. Maybe every black line here in this series of concentric circles, concentric meaning having the same center, concentric. These concentric circles are